Hi, in this lecture we are going to study NP hardness reductions. Let us begin with a definition. We are going to define by P the class of problems that can be solved in polynomial time in the input length. So if your input length is n, then a problem is in P if it can be solved in time n to the c for some constant c. Think of c as being 2, 3, or maybe even 100. The idea is that if a problem is in P, if it's easy, and if it's not in P, it is hard. So P is supposed to capture our intuitive notion of easy problems. Now, some problems in P can be really hard, actually. For example, if this constant c is equal to 100, but the focus of this lecture will be on showing that things are difficult. So if you show that a problem is not in P, then it means that it cannot be solved even with the constant c being equal to 100, and so it should be really hard. So ideally, we'd like to show that many natural problems are not in P. We'd like to classify problems in easy and hard. However, remarkably, it is not known how to do that. Okay? And this is related to the P versus NP problem. So what we do instead, we're going to link the hardness of the problems. We're going to establish connections or reductions. So what we do next, we're going to define several problems, such as set, clique, and subset sum. And we're going to prove connections or polynomial time reductions among them. A polynomial time reduction is a fact of this type, that a problem clique is in P, so it can be solved in polynomial time. Then this implies that also the set problem is in P. Okay? Or another reduction would be that if subset sum is in P, then also set is in P. And we're going to use the terminology A reduces to B in polynomial time if it is the case that B is in P implies A is in P. Okay? Don't get confused with this terminology. If A reduces to B, then that means that if B is in P, then A is in P, not the other way around. So why are we doing this? We're doing this because if you encounter some problem X, okay, instead of trying to show that X is hard, that nobody can do unconditionally, instead you can try to find a problem Y that people think is hard, and then you can try to reduce Y to X, okay? And if you succeed, then you have a high degree of confidence, perhaps, that X is hard as well, and you can move on. So here is the map of the reductions that we're going to see. And an arrow from A to B here means that if A is in P, then also B is in P. Okay? The first reduction that we see is that if clique is in polynomial time, then 3sat is in polynomial time. And the first thing that we need to do is to define the problems 3sat and clique. So let us start by defining 3sat. So let us start by defining Boolean formulas. So a Boolean variable is a variable that takes two values, either true or false, 1 or 0. Okay? A literal would be a variable or its negation, like x and not x. And a clause is an OR of literals, like X or not Y or not Z. A CNF is a formula in conjunctive normal form, is an AND of clauses, like X or not Y or Z. This is one clause, and Z, this is another clause, and not X or Y. This is another clause. And finally, a 3CNF is a CNF where each clause has 3 literals. For example, X or not Y or Z, and Z or Y or W, and not X or Y or not U. And a 3CNF is satisfiable if there exists an assignments of 1 or 0 or true and false to the variables that make the formula true. For example, is this CNF here satisfiable? It is, because if you set X to 1 and Y to 1, the formula is satisfied. That is, each clause would be true. Okay, for example, the first clause would be true because X is equal to 1, so this whole thing here is true. The second clause would be true because Y is equal to 1, so the whole thing is true. And the third clause, for example, has not X. This is not helpful because X is 1, so this thing will be 0. But has also a Y, so the whole thing is satisfied. Okay. The problem 3-sat is the problem of deciding if a given 3-sat formula is satisfiable. Okay? So in this lecture, we're going to use the set notation. So we just define 3-sat to be the set of formulas which are satisfiable. Otherwise, it is just the problem given a formula phi, determine if it is satisfiable or not. And phi is a 3CNF. So here is an example. Is this formula here satisfiable? And the formula is satisfiable because if you set X to 1 and Y to 0 and Z to 0, you get 1 or 0, and 0 or 1 or 0, which is 1 and 1, which is 1. So the formula is satisfiable. Is this formula here satisfiable? The second formula is not satisfiable because it's of the type X and not X. So no matter how you set X, you will not satisfied. If you set X equal to 0, you will get 0 and 1, which is 0. If you set X to 1, you will get 1 and 0, which is equal to 0. So people believe that 3-sat is hard. They believe that 3-sat is not in P, and as I mentioned earlier, nobody knows how to show that. The best known algorithms that we have for 3-sat takes time which is exponential in the length of the formula. Okay? So in particular, they are not polynomial. Okay, after having defined 3-sat, we can now define the clique problem. So a graph G has a set of nodes V, also known as vertices, and a set of edges E that connect pair of nodes. Here is an example of a graph. And we define a t-clique in the graph to be a set of T nodes which are all connected. For example, this graph here is a 5-clique because every pair of nodes is connected. The clique problem is you're given a graph and a parameter t, and you want to know if the graph G contains a t-clique. For example, let's look at this graph. Does this graph contain a clique of size 3? Is G3 in the clique problem? And the answer is yes, it is, because this is a clique of size 3. Every pair of nodes is connected. Let's look at this other graph H. Does this graph have a clique of size 4? And the answer is no. You cannot find 4 nodes here which are all connected. If you take these 3, for example, these 3 are all connected, but if you pick another node like this edge here would be missing. Again, people believe that clique is difficult. The clique is not in polynomial time. And we don't know how to show this, but we can show that there is a relationship between clique and SAT. Okay? So 3SAT and clique are both believed to be hard, not in P. They seem to be different problems at first sight, and yet we can show the following theorem, that if clique happened to be easy, then also 3SAT would be easy. Okay? So in particular, if you think that the 3SAT is difficult, that 3SAT is not in P, then you also think that the clique is difficult, the clique is not in P. Now, this theorem here gives what type of reduction? Okay? It gives a polynomial time reduction of 3SAT, from 3SAT to clique. Okay? So if clique is easy, then 3SAT is easy as well. Okay, we want to establish this theorem that if clique is in P, then 3SAT is in P. And here is our proof outline. We are going to exhibit an algorithm R for reduction, R, that given an input, a formula phi, is gonna transform or translate the formula phi into a graph g phi and an integer t phi, such that the formula is satisfiable if and only if the graph g phi has a clique of size t phi. Okay? Equivalently, g phi t phi is in the problem, is in the set clique. And R should be efficient. Okay? Should be a polynomial time computation, a polynomial time algorithm. Okay? So why exhibiting such an R is enough to prove the theorem? Okay? It is enough to prove the theorem because if you had some algorithm C that solves clique in polynomial time, then this new algorithm here will solve 3SAT in polynomial time. What's the algorithm? If you give me a formula phi, first I'm going to feed phi to the translation, to the reduction, to the transformation R. R is going to take phi and transform that into a graph and a number, into a pair gt, and now you're going to feed this new pair g and t into the algorithm C. The algorithm C is supposed to solve clique, so you will be able to know if the formula is satisfiable, because the phi is satisfiable if and only if g phi has a clique of size t phi. Okay? And this is the same outline that we're going to follow in all these problems. Okay, so here is the definition of R. Let us first see the definition, and then we're going to see a picture. So the input to R is a 3CNF formula. Okay, so it's a formula phi of this type, A1 or B1 or C1, and A2 or B2 or C2, and so on. Each of these things is a clause, and we have K clauses. So we go all the way to AK or BK or CK. These AI, BI, CI are literals, so they can be either a variable or the negation of a variable. Given phi, the algorithm R is supposed to transform or translate phi into a graph and a number. A graph g phi and the number t phi. And the way it's done is as follows. The nodes of the graphs will be the literals of the formula. And as edges in the graph, we are going to connect all the nodes except those that fall in two categories. We are not going to connect the nodes which correspond to literals in the same clause. And we are also not going to connect nodes which are contradictory, such as x and not x. Okay? And this completes the definition of G. The reduction also has to output a number t phi, and this number t phi is set to k, the number of clauses in phi. Here is an example. Here is a formula with 3 clauses, and here is the associated graph. We have nodes x, y, z for the first clause. We have nodes not x, not y, and z for the second clause. And we have nodes x, y, not z for the third clause. Okay? So, which edges do we put? So as we mentioned earlier, we're going to put every edge except those in 2 categories. We are not going to connect edges between nodes in the same clause. So I don't have this edge here, for example, or this edge here, or this edge here. And I'm not going to connect nodes which are contradictory. So for example, I'm not connecting x to not x, or not y to y, or z to no z. Every other pair is connected. This z is connected to y, this x is connected to z, and so on. And the clique size that we're asking for is 3. Remember, clique size is 3. Okay, so the claim that we make is that in this graph, we have the following. So if the formula is satisfiable, then the graph g phi has a clique of size t phi, and vice versa. If g has a clique of size t, then the formula is satisfiable. And here is the high-level view of the proof of the forward direction. We're going to suppose that phi has a satisfying assignment, and we're going to show a clique of size t phi in g phi. So let's see the proof first, and then we will go back to the picture and show it in pictures. So let's do this proof. Let's suppose that phi has a satisfying assignment. Okay, so what do we know? We know that each clause must have at least one true literal. Okay, this is what is given to us. This is given to us. Now it comes the creative step in this proof. Okay, we're gonna exhibit a clique in the graph. Okay, so we're gonna pick the corresponding nodes in g phi. Okay, we know that each clause has one true literal. You're gonna pick the corresponding nodes in g phi. So how many nodes do we pick? First of all, we're gonna pick k nodes, right? Because we set t equal to k. This means that we have enough nodes for our clique, because we're asking for cliques of size t. Okay. Now we just need to verify that these nodes form a clique indeed. Okay. And they are a clique because we connect every pair of nodes except those in 2 categories. Those in the same clause and those which are contradictory. So let's ask ourselves, did we pick any 2 nodes in the same clause? No, because we are picking nodes, right, one from each clause. Our nodes are picked from different clauses. Now, can our nodes be contradictory? And here is a critical step. They cannot be. Why? Because the nodes correspond to true literals. True literals. Now, if x is true in an assignment, it's not possible that also not x is true. Okay? Hence, the nodes that we pick are connected. Okay? Our nodes correspond to true literals in an assignment. If x is true, then not x cannot be true. Okay? And we also need the reverse direction. Okay? We need to show that if g phi has a clique of size t phi, then we can exhibit a satisfying assignment for phi. Okay, we're going to suppose that g phi has a clique of size t phi, and we're going to show a satisfying assignment for phi. Okay, So let's suppose that we have a clique of size t for a jiffy. First of all, we need to observe that we have some structure in this clique. First of all, we remark that we have exactly one node per clause. Why is this? Well, it's because we did not connect any nodes within the same clause. Okay, so if we start with a clique, we cannot have two nodes in the same clause. Okay. Given this, we are gonna define an assignment for the formula phi. The assignment that we define is such that those literals are true. Okay, I pick those literals and I make them true. Now, I can do this as long as I don't have contradictory literals. If I have x and not x, I couldn't make them both true. But that's not the case. That doesn't happen because in our graph, we do not have edges between contradictory nodes, between contradictory literals. So I can indeed make all these nodes true. Okay, it's possible because contradictory literals are not connected. So this assignment will satisfy the formula because we have exactly one node per clause. Okay, those nodes are made true, so every clause will have a true literal. Every clause will have a true literal, and every clause is satisfied. Let us see this with the example. Here is the example from before. Okay, here is a particular assignment. X is equal to 0, y is equal to 1, and z equal to 0. You see what happens in these clauses. Okay, so this clause here would be 0, 1, 0, going with 1, 0, 0, and so on. Okay, so we need to pick one true. So now we are going to exhibit a clique in the graph. Okay, so we're going to pick one node per clause. Okay, and we're going to pick one node which corresponds to a true literal in the assignment. So from the first clause, we have y, which is true. We're going to pick this node here. From the second clause, we have not x, which is true. So we're going to pick this node here. And from the third clause, we're going to pick not z, which is true. Okay, so it's this node, and this node. And we see that we do have a clique of size 3 with these nodes, okay, because these three edges here are present. Okay, so starting with an assignment, we have exhibited a clique of size 3 in the graph. 3 is our target size because we have 3 clauses. So we ask for cliques whose size is the same as the number of clauses in the formula. And this is not the only possible assignment. This is a different assignment. Okay, x is equal to 1, y is equal to 0, and z is equal to 1. Okay, and this gives different literals which are true, and it gives a different clique in the graph. For example, from the first clause, we can pick the literal z. From the second, we pick not y. From the third, we pick x. And again, I would have a clique here. So every assignment which satisfies the formula gives rise to a clique of size, the number of clauses in the graph. Okay, so let's go back to our theorem. We are showing that if clique is in P, then 3sat is in P. And the proof outline, remember, we gave an algorithm R that on input phi computes a graph g phi and an integer t phi, such that phi is in 3sat, phi is satisfiable if and only if the graph g phi has a clique of size t phi. Okay, so far we have done this. We have done this part here. This was done just now. Okay, we are not quite done because we also need to verify that R runs in polynomial time. We need part 2. Okay, now 2 is somewhat obvious if you just think of how R was defined. Okay, somewhat less interesting. Still, we have to verify it. Okay, remember the definition of R that we saw earlier. Okay, it's right here. Okay, we need to show that R runs in polynomial time. We are not going to directly count the steps of the algorithm. We give a more high-level argument. So what does R do? Well, to compute the nodes is going to examine all the literals. The number of literals is at most the length of the formula, which is of course a polynomial in the input length. In fact, it's linear in the input length. To compute the edges, we have to examine all the pairs of nodes. Okay? And the number of pairs of nodes is the most quadratic in the number of nodes. Okay? Which is at the most quadratic in the input length, which is the length of the formula. Okay? So even to compute the edges, we only spend time, which is polynomial in the input length. Overall, the time is about linear in the length of the input plus quadratic in the length of the input, which is a polynomial in the input length of the formula, and this concludes the proof. So now we have finally established completely this theorem. We have concluded the proof of this theorem. Again, the outline was to give an algorithm R, which on input phi computes a graph G and an integer t, such that the formula phi is satisfiable if and only if the graph has a clique of size t. Okay? And moreover, R should be efficient, it should run in polynomial time.